And the very last thing I'd like to say on this topic, this is Proposition 2.3.8. It's that if I is an interval, and you've got a function from your interval to the real numbers, is injective and one-to-one, and continuous. So Proposition 2.3.9 was about strictly monotonic continuous functions. This proposition is saying that you don't need to check that f is strictly monotonic. If it's continuous and injective, then it has to be strictly monotonic. There aren't any one-to-one continuous functions on intervals that are increasing for a while and then decreasing after that. Now, to prove this proposition, we'll need a lemma, and here is the lemma. Let's suppose you've got two numbers, two real numbers. We're going to let a be the smaller one. They're not equal. And f is a function from a to b to the real numbers, is injective, and also continuous. Then one of the two things has to be true. We've got that f of a is the lowest point and f of b is the highest point. Or it's the other way around. This isn't quite Proposition 2.3.8. This is showing that it's strictly increasing if you insist on looking at just one of the endpoints. So here is our proof. By the extreme value theorem, which we saw earlier in section 1.7, there is there are two numbers, x and z in AB, such that we've got f of x less than or equal to f of y less than or equal to f of z for all y in our closed interval from a to b. And because f is injective, we could make this strict inequality is if we insist that y is not allowed to be x or not allowed to be z, but let's leave it as a less than or equals to include the yz case. So let's suppose, this is for the sake of contradiction, that x is not one of the endpoints. So that's a is strictly less than x is strictly less than b. And I'll draw you the picture of this. Should be clear after that why that can't happen. Here is A, here is B, here is X. Then here is f of x, and then because f of x is the low point, f of a and f of b both have to be above f of x. And then because it's continuous, we've got to go like this. And then if we picked a number in between here, let's call it tau, then we see we've got 2 points. Hence, C and D here, where f of C is f of D is tau. Let's make that argument rigorous. So let's let then f of A is greater than f of x. F of B is also greater than f of x because f is injective, so they can't equal f of x. And so because f of x is less than or equal to f of y for all y in our interval. So now what we're going to do is we're going to let tau be f of x plus 1/2, whichever is smaller, f of b minus f of x, and f of a minus f of x. Then we have that f of x is less than tau, is less than f of a, and also f of b. So by the intermediate value theorem, tau is f of c and is also f of d for some c between a and x and d between x and b. And then c is not equal to d. One's less than x, one's bigger than x, but f of c equals f of d. So f is suddenly not injective. And that is a contradiction. And similarly, z is equal to a or z is equal to b. So the high point is either a or b. And x is not equal to z because if they were, if f of x equals f of z, then f would have to be constant. F of x would have to be f of y and f of z for all y in this interval a to b. So f is not constant. sorry, not injective. Same proof of by contradiction as before. So either x is A, z is B, and f of A is less than f of y, is less than f of B for all y between A and B, and by throwing out the endpoints A and B, we can ensure that it's a strict inequality. Or other way around, A is Z, B is Y, and we've got strict inequalities in the other direction. And that's what we were trying to prove. And now let's prove proposition 2.3.8 in the case where your interval I is closed and bounded. And we'll leave the case where it's not closed or not bounded. We'll leave that as a homework or possibly exam study problem. So first off, if I is the empty set or a single point, those are called trivial intervals sometimes, then there's nothing to prove. Any function on the empty set or on a single point, what does it even mean for that to be strictly increasing? Strictly increasing is all about picking two different points in the domain and seeing what happens. And if there aren't two different points in the domain, there's nothing to prove. And so we can look at the case where I is a non-trivial closed interval. And let's name the endpoints C and D. And then we know by our lemma either f of C is less than f of y is less than f of D, or inequalities go the other way. And let's suppose we're in the first case, the case where we really hope our function is increasing. It's a very similar argument in the other case. So let's let x and z be in our interval from C to D, and let's let x be the smaller of the two. And so we can draw this. We've got our points, our endpoints C and D, and our middle points. X might be C and Z might be D, but they can't be equal to each other. And then by the lemma, then we have that f of C is less than or equal to f of x. We know that because x is between C and D, is in our interval. So then apply the lemma now not on the interval from C to D, but now from C to Z. And then X is between, either X is equal to C or X is between C and D. So we've got that either f of C less than or equal to f of X strictly less than f of Z, or f of C is greater than or equal to f of X is strictly greater than f of Z. But f of C is less than f of Z is less than f of D because Z is between C and D. So we have f of C less than or equal to f of X is less than f of Z. And since X and Z were arbitrary, we have that f is strictly increasing. And similarly, if f of C is bigger than f of Y, bigger than f of D, for all Y in CD, we have that f is strictly decreasing. And in either case, f is strictly monotonic, so that's what we wanted to prove. All right, I know I said that Proposition 2.8 to 3.8 was the last thing I wanted to say on this topic, but now that I think about it, I don't really want to start limits, which are the main point of Section 2.1 in the middle of a video like this. So let's say a bit more about increasing and decreasing about monotonic functions. This is Proposition 2.1.9. So we're going to let X be a domain and f be a function from our domain to the real numbers. And let's suppose f is monotonic. And the conclusion is that then f doesn't necessarily have to be continuous, but it does have to have at most countably many discontinuities. So let's prove this. So in this case, the notation is going to be a bit messy. So I'll define our notation and then we'll talk about it, what it means. Let's let C be a point in our domain X. And then if C is equal to the supremum of all points in X that are less than C, we're going to let f of C minus be let's specify now that we're taking f to be increasing. It's monotonic, so it is either increasing or decreasing, and the notation will be a lot clearer if we just pick increasing. And I'll point out, if we've got a decreasing function f, you can multiply by -1. That'll turn it into an increasing function. What we're about to prove that increasing functions have countably many discontinuities. Multiplying by -1 again will turn it back into the decreasing function you started with and won't introduce discontinuities. So we'll let f of c minus be the supremum of all f of x, where x is in x and x is strictly less than c. And conversely, and similarly, if c is the infimum, we'll let f of c plus be the infimum of f of x, where x is bigger than c. And let's draw a picture of what it's going on here. Here is our point x. Here is f of x. And then because this is an increasing function, our picture is going to look like this. You can here is f of c minus. Sorry, this point is named c, not x. And then f of c plus is up here. And now I've got this funny condition that c is where, or I'm requiring that c be the infimum or the supremum. What I'm trying to avoid is this case. So here is our domain x, and let's say c is an endpoint. And we've got f of c here. Then we're increasing. And then notice that we've got this big vertical horizontal gap here, and we sort of don't care about that. So in this case, we're going to let f of c be f of c plus if c is strictly less than the infimum of our x's in our domain that are greater than c. C is obviously a lower bound on this that I wrote down, but if it's not the greatest lower bound, we're going to let f of c plus be just plain old f of c. And we're going to use a very similar definition for f of c minus but I think I won't write that down. And then I want to claim, and then I have two claims. So here is my first claim, and that's that if f of c minus is equal to f of c and is also equal to f of c plus, then f is continuous at c. And my second claim is that there are at most countably many points C in our domain X where the previous thing is false. And then there are at most countably many points where we don't have this equality. That means there are at most countably many points where f is not continuous, which is precisely what we wanted. So once we've proven these two claims, we'll have proven the proposition. So let's prove our first claim. So let's let C be a point in X such that our condition is true. And we want to show that f is continuous at C, so we're going to do that by, we're going to pick a positive number epsilon. And then epsilon delta characterization of continuity, we want to find a delta such that if C minus X is less than delta, then f of C minus f of X is less than epsilon. Now, f of C minus equals f of C. There are two ways that can happen. So let's look at those two ways. If f of C is equal to f of C minus is equal to the supremum of our f of y x such that x is less than C and is also in our domain, then f of C minus epsilon is not an upper bound. It's less than the least upper bound, so it's not an upper bound. And then we're going to let y be in X, y is less than in C, but f of y is greater than f of C minus epsilon. And such a y must exist, otherwise f of C minus epsilon would be an upper bound. And we're going to let delta 1 be C minus y. Y is less than C, so delta 1 is greater than 0. And then notice that if C minus delta is less than X is less than C, then we have this long chain of inequalities, f of c minus epsilon, that's less than f of y, which is equal to f of c minus delta 1. Sorry, but y is equal to c minus delta 1, and so y is less than x. So because we're increasing, this is less than or equal to f of x. And then because x is less than c, f of x is less than or equal to f of c. So in this case, we've got that f of x minus f of c is less than epsilon. Remember, there is another way this can happen. So if f of c equals f of c minus, because c is not the supremum of the points that are of the points in our domain that are less than c. And notice that c obviously is an upper bound, so if it's not the supremum, then it's not the least upper bound, then it's greater than the least upper bound. In this case, we're going to let delta 1 be c minus the supremum, and because this is a strict inequality, delta 1 is positive. And then if c minus delta 1 is less than y is less than c, then, well, y is bigger than our supremum. So, and if you're bigger than a supremum of the set in particular, you can't be in the set. But x is not, but y is less than c, so y is not allowed to be in our domain. So if c minus delta 1 is less than y is less than c, and y is in x, well, there are no such points, so I can write down anything I want and have this be true. We say this is vacuously true. That's the term for a statement that starts with for all, and then you list off a kind of set that there aren't any of. F of y minus f of c is less than epsilon for all none of the points y that are both in our domain and within delta 1 of c on the left-hand side. And coming back up here, I see I have forgotten to specify that x is in our domain. We do need that for f of x to be well defined, but you get to require that in the definition of continuity. And then you do a similar argument for the right-hand side. If f of c is f of c plus, let delta 2 be either the infimum of points in our domain that are bigger than c minus c, like in the second bullet point, or let delta 2 be z minus c, where z is in our domain, z is greater than c, and f of c is less than our is less f of z, is less than our infimum of f of x. Plus epsilon, also known as f of c plus epsilon. And then in either case, if c is less than x is less than c plus delta 2, and x is in our domain, then we have our condition for continuity, f of x minus f of c, that is strictly less than epsilon. So now let's let delta be whichever is smaller, the left delta or the right delta, and then if x is in our domain with x minus c less than delta, then there are only three ways this could happen. The only possibility is, so either x is less than c, in which case, because the absolute value is c less than delta, we must have c minus delta is less than x, but then we have c minus delta 1 is less than x. So f of x minus f of c is less than epsilon. Second possibility is that x is equal to c, in which case f of x minus f of c is 0, is less than epsilon, because epsilon was positive. Or final possibility, we've got that x is bigger than c, then it must be less than c plus delta, meaning less than or equal to c plus delta 2. So in this case, we again have that f of x minus f of c is less than epsilon. So in any of these cases, f of x minus f of c, that thing is less than epsilon. Now let us prove our second claim. So let's suppose that f of c is not equal to f of c minus. And the only way that can happen is if f of c minus, it necessarily has to be the supremum of f of x, such that x is in our domain and also x is less than c. If the other definition, you always have that f of c equals f of c minus. And that implies, notice that f of c has to be greater than f of c minus, because f is increasing, so if c is bigger than x, then f of c has to be at least f of x. So f of c has to be an upper bound of this set we are taking the supremum of. And then similarly, if f of c is not equal to f of c plus, then because f is increasing and c plus is an infimum, f of c has to be less than f of c plus. So if it is false, that f of c minus equals f of c equals f of c plus, then f of c minus, that has to be strictly less than f of c plus. So now we know a little bit about the points where f of c is not the same as f of c plus or f of c minus, which, remember, every point where you're discontinuous is like that. So now let's say one other thing. Let's let c and d both be in our domain. C is less than d, and f is discontinuous at both c and d. So f of c minus is less than f of c plus. F of d minus is strictly less than f of d plus. All right. Now, what can we say? So if f of c plus equals f of c, and f of d minus equals f of d, then we have this chain of four inequalities. F of c minus less than f of c. It's less than c plus, less than or equal to f of d minus, because d minus is the same as f of d, f of c plus is the same as f of c, less than f of d plus. And this is true because f of c plus equals f of c, and f of d minus equals f of d, and because c is less than d and f is increasing, we get the middle inequality. And if this is not true, f of c is strictly less than f of c plus, we'll put the argument for this case, but very similar argument works. If f of d minus is strictly less than f of d, then let y be in our set of points in our domain that are greater than c, and notice that that if f of c plus is different from f of c, then c is the infimum of this set, so we can require that y be less than c plus any positive number. In fact, we can require y be less than d. And y exists because d is greater than c, which is the supremum of that set. So d, as usual, is not not supremum, infimum. So d is not a lower bound. And then f of c plus is the infimum, recall, that's necessary. That can't be any smaller than f of y because y is in the set we're taking f's of. And then similarly, because y is less than d, we have that f of y is less than or equal to f of d minus. So in this case, we also get our long chain of inequalities, f of c minus less than f of c plus is less than or equal to, and here we've got an f of y in the middle, and then we've got an f of d minus less than f of d plus, and that's very much like what we had before, except we've got some slightly different auxiliary things.